This is our introduction to systems of linear equations. So this is where it's kind of like you're solving two equations at the same time. And we have a way to do it algebraically, but first we're going to do it just by graphing. It's kind of more of an intuitive way to look at this. So here's what it is. So here's some technical mumbo jumbo. A system of linear equations is a group of two or more linear equations where each equation contains one or more variables. So it could be 3, 4, 5 different linear equations, okay? And it could have 3, 4, 5 different variables. For right now, we're just going to have two equations and two variables. The techniques that we're using now can be extended into more dimensions, I guess, but don't worry about that. So for now, just think of a system of linear equations as being two equations, both of which have like an x and a y in them, and we'll do nothing but examples. So there's one. 2x plus y equals 1 and negative x plus 2y equals 12. That's a system. It's got two equations, and it's got two variables. And what we'll find is there's generally going to be a unique solution to this, but the solution is going to have two components to it. It's going to have a solution for x and a solution for y. So there's some specific unique x and some specific unique y that satisfies this system, meaning that it solves both equations. And so we're going to write that solution as an ordered pair. Now you can just write x equals 5 and y equals 4, whatever it happens to be. But for now, it's good to think of it as an ordered pair because that's how we're going to visualize it. Okay, so the solution isn't just x equals this or y equals this. It's two things. Okay, so here's a little bit of philosophy. So the system represents two lines. In other words, 2x plus y equals 1 is a line, and you know how to graph it. Negative x plus 2y equals 12 is a line. So those are two different linear equations. So look at the first one, 2x plus y equals 1. All of the points that work for that satisfy that first equation, sit on a line. And that's really the points on that line, that's what they represent, the solutions to that first equation. Okay, for that second equation, that's a different line. All the points that sit on that line represent all of the different solutions to that equation. So if you think about two lines floating around in space, what are they probably going to do? They're probably going to intersect, unless they're parallel. They're going to intersect at one unique tiny little point. So that point where they intersect is the only point that sits on both the lines, right? So that point represents a solution to the first equation and it represents a solution to the second equation. So that point represents the solution to the system. So visually, all we have to do is graph the first line and graph the second line together, see where they hit each other, where they intersect, and that's our solution. And that's the first way we're going to tackle it. So let's just do the one we already have on screen. Graph 2x plus y equals 1. We've been over how to graph lines. You know, you can probably be using a calculator now. This is y equals negative 2x plus 1, so you should know how to graph that by hand. It's a line with slope negative 2 and y-intercept 1. Either way, we want our graph to be pretty much perfect. So either you're going to graph it using grid paper or something, or probably use a calculator, or just follow along with me. So there it is. So however you did that, I don't know. So now we're going to graph negative x plus 2y equals 12. Remember, to graph this with a calculator, you need to solve it for y anyways. So you'd get like 2y equals x plus 12, so y is 1/2 x plus 6. Is that right? Yeah, that's right. Okay. So however you did that, there it is. And so again, the nice thing about using software, a computer, a calculator or something is we're sure. It sure looks like these two lines intersect at this point I'm pointing to, which is the point negative 2, 5. Now, if it were a tiny bit off from that, if it were like 4.99 instead of 5, that would be annoying because we wouldn't know that. We would just assume it was 5. But assume for right now, I'm not trying to trick you, and it is what it looks like. Okay, so it is. It is. So the point negative 2, 5 is where these two lines intersect, which means when x is negative 2 and y is 5, both of these equations are satisfied. And the nice thing about this is we can check it. So it has to work for both equations. So for the first equation, plug it in for x, -2 for x, and then 5 for y is -4 plus 5, 1. Yes, a Rooney. And then for the second equation is, okay, -2 plus 2 times 5 is what? 2 plus 10, which is 12. Okay, there you go. So we found it. So you see how we did that visually? We find where the two lines intersect. That point sits on both of the graphs, which means it satisfies both of the equations. So there's a million points that just satisfy one of the equations, but this is a little different. Now we're looking for an ordered pair that's a solution to two equations at the same time. Right, and then that's important to note. I mean, just visually, are these two lines ever going to intersect again? No, because lines don't curve unless you're talking about like the theory of relativity, which we're not, okay? But think about any two lines you put on a plane, they're only ever going to intersect once, unless they're parallel, in which case they're going to intersect never. But in most cases, you're always just going to have one unique solution. And that's the case for pretty much no matter how many equations you have in your system. Although, again, we're just messing with two. Okay, let's do another. If you're happy with what we just did, I would pause the video and try this on your own calculator. Your calculator certainly has a way of doing an intersect if it's not obvious just from looking at the graph. Again, these should all be integers, so assume it's not going to be like something tricky where it's, you think it's one thing and it's another thing. Okay, so that's our system. Y equals 2x plus 4 and 2x minus y equals 1. So the first one's already easy to graph. It's already in slope-intercept form. The second one would be pretty easy. You'd get what y equals 2x minus 1. Or again, if you're using a computer, you can just type that stuff in. I use GeoGebra for all the graphs I make in this class. You can ask me about that sometime. You can just type that in and it'll graph it for you. So there's the first one, slope of 2, y-intercept of 4. There's the second one, slope of 2, looks like y-intercept of -1. Okay, and now you see, remember before where I said, okay, the only way for these two lines not to intersect is if they're parallel. Well, look what we have. These two lines are parallel. And you actually, if you graphed them by getting y by itself, you already knew that. You already knew that they both had slope too. And they have different y-intercepts, so they are two different lines, but they never intersect. Okay, and then convince yourself that's the only possible way for a system like this to not have any solutions, if the lines are parallel, right? There's no other way for two lines not to intersect. So that's just it. We've seen this type of thing before. The system just has no solution. That can happen. So remember, you can just write no solution for me, or you can put the fancy little null set symbol if you want. The homework might make you do that. So this is a word that specifically refers to systems of more than one equation. Just if you see that word in the future, the system is inconsistent, it means it doesn't have a solution. And in all other cases, it's consistent. So obviously most of the systems we're going to look at are consistent because it's pretty boring just to do a bunch that don't have any solution. All right, one more, and we're going to see just the one more little thing that can happen here. And then that's it. And then we're going to dive right into solving these, doing actual algebra, right? Because that's the name of the class. Okay, so again, just however you have to graph these two lines, 3x minus y equals -2 and -6x plus 2y equals 4. There's the first one. Okay, so I threw it up on the screen. That one's got, looks like a slope of 3, yeah, slope of 3, intercept of 2. And here comes the second one. That's not a mistake. There's the graph of -6x plus 2y equals 4. Well, why don't you see the other line? Think about it. Look at these two lines. They're actually multiples of each other. If you take this first one and multiply it by -2, you would just get the second one. And if the way you graph this system was to set everything, get y by itself and get it in y equals mx plus b form, you would see when you simplified it that they're actually the same exact line. So if you just multiply both sides of a line by whatever, it's still the same line. So it wasn't obvious, the way it was given to us before. But these two lines are the exact same line. Right. If you did it that way, you'd see that they were both equal to 3x plus 2. Okay, so this is a little weird because we don't have a unique solution and we don't have no solutions. We actually have an infinite number of solutions so they're not really the same equation, but they are the same, right? They look different, but they are the same line. So this is, I guess, what you might call like a redundant system, but we still will see this and we need notation to express the solution. So the solution is this: any point that sits on either line. And since they're both the same, really anything that jives with y equals 3x plus 2 is a solution to the original equation. So it's not just like the original system. So it's not just like any ordered pair satisfies it, right? Just the point like 2, 3 doesn't satisfy it. It doesn't sit on the line. But any point that sits on the line satisfies it. So here's, rather than saying just literally this, any point that sits on either line, we have to have a mathematical way of saying that. So here it is. So here's how we write that down. So this is set notation. Remember, these braces or fancy brackets denote a set. So I'll make it clear what all this stuff means. But this, so you put it in a set because it's a set of solutions. This means any ordered pair xy. The little vertical line means such that, okay? So this says any xy such that 3x minus y equals -2. So I just used the first equation. So what this says is, it really says this: any point that sits on this first line. You could also say any point that sits on the second line because you know they're the exact same line. You could also say any point that sits on this line because that's just the same lines, just cleaned up. So you could say any xy such that y equals 3x plus 2. Okay, so that's the new thing. So your book, I think, talked about this back when we talked about sets and inequalities. I kind of skipped it because we really didn't need it then, but we kind of need it now and going forward. So this is the way you say that out loud. Any x and y such that 3x minus y equals -2. So right, your solution is a set. It's an infinite set of pairs of numbers. So you just have to specify what form those pairs of numbers take, and that's it. So you put either of your beginning equations in here. Or if you already cleaned it up, you can put that into if you think that looks nicer. So when you get a system like this that's it's almost trivial, it's like a lot of numbers work, this is how you have to write it down. If you just straight up wrote in English any point, like if you literally wrote this down, I'd give you some credit, but I am going to want to see this notation on the next exam because, because we need it. This is the proper math notation. So that's called set notation. And the more we see it, we'll see it in other contexts. Okay? Thank you.